Thank you very much. I'm very honored to speak at this remarkable conference. I know Yura for many years. We worked together at the chair of higher algebra of Moscow State University, teach students together. We participated in many conferences. We met many times in Tübingen in Germany, in Grenoble in France. In Moscow, yes. Unfortunately, we don't have joint paper. And in fact, once in Grenoble, Yura proposed me, let us think together about these things. And I missed this opportunity. I didn't use it. I regret up to now. But I asked Yura many questions, and he always, for him, this is an easy question. But for me, it was very important to know the answer. And I learned a lot from him, and I'm very grateful to him. And returning to the talk, I don't like slides very much. I'm sorry for this presentation. I always try to use Blackboard. But this time, I decided that since we have online participants, maybe it's better to produce slides, and that is why I use Beamer. OK, so my talk will be mostly about additive actions. But I would like to start from some general picture from this covering of algebraic varieties, just as some motivation for additive actions. Oops, this way. My field, my ground field, always will be an algebraically closed field of characteristic 0. I consider an abstract arbitrary algebraic variety over X. And by definition, any algebraic variety is glued from open affine charts. So there are some open affine subsets, and my variety is a union of these subsets. I would like to recall the definition which was yesterday, but which was given in Michael Zeidenberg talk. X is called uniformly rational if we have a specific covering. If we can cover our variety by open subset, which are isomorphic to open subset of affine space. Obviously, in this case, the variety is smooth. In this case, the variety is rational. And the opposite direction is a famous conjecture, which is open up to now. If you have a smooth rational variety, is it true that it is uniformly rational? In fact, very natural question. Because if you have a smooth rational variety, may you have locally something different from an open subset of affine space? And this is not known. But there are a lot of positive results that in many cases this is true. And also, this class of variety is stable when we blow up a smooth variety. And this shows that we may produce many, many examples of varieties with this property. In fact, we use this class of variety in our joint paper with Kaleman and Zeidenberg. But Mikhail Grigorich reported on this yesterday, and I will not repeat it. One step further. Let me say that variety is A-covered if we can choose this open chart to be just affine spaces. By coincidence, this is exactly what was mentioned at the end of previous talk. So this is an algebraic variety in a naive sense. Like in differential geometry, what is a differential manifolds? This is just a gluing of local subsets which are Euclidean spaces. So here affine spaces as well are taken. In Gromov terminology, this class also was mentioned in Gromov paper of 1819. This is called of class A0. This class of variety is also preserved under blowing up, but this time we should be careful. We should take subvariety which are linear with respect to these affine spaces which cover our variety. But you can prove that all smooth projective rational surfaces have this property. This is stable under blow up of points. Yesterday it was mentioned that all smooth complete toric varieties, smooth complete spherical variety have this property. And we have a result joined with Alexander Perepechko, who is here, and Hendrik Zeus, that more generally, any smooth complete rational variety with a T action, but not necessarily with an open T orbit, but we allow the case when generic T orbit have codimension 1. This is called complexity 1. They are also A-covered. And very nice result, also mentioned yesterday. This is a recent result of Prохорова and Zeidenberg. It concerned Fano Mukai fourfold of genus 10. And here is one exception. And this one exception also, yesterday we learned how to treat this example. This is not A-covered, but there is some specific covering. But nevertheless, it shows that there is no conjecture that any, say, complete smooth rational variety is A-covered. This is not true, because we can construct smooth, rational, complete varieties which cannot be covered by a affine space. Okay? And maybe some results which one can consider as motivation for considering covering. Certainly, covering are responsible for local properties. If you know all affine charts, then we know locally what is around each point. But we can find also some global result about variety. The first one is classical Kleinman-Chevalier criterion, which says that if you take a smooth variety, if it is quasi-projective, then it's very easy to find open subset, a fine open subset which contains a given finite subset. Say you take your variety, you take finite set of points, and you want to know, is there a fine neighborhood which contains this finite subset? And it turns out that this is the case if and only if the variety is quasi-projective. There are some generalization to non-smooth case, but it will be more technical, and I'm not ready to discuss it now, but I would like to also recall a result by Volodarczyk that for normal variety, we can weaker this requirement. We can ask that not any finite subset, but any 2 points are contained in an open affine subset. And this is equivalent to embeddability into toric varieties. So what are projective or quasi-projective? Embeddable into a projective space. But we replace projective space by an arbitrary toric variety and ask which variety live in toric varieties. And this turns out that this is equivalent to existence of a fine open neighborhood for any 2 points. And there are varieties which do not satisfy this condition, which are not embeddable into any toric variety. They can be constructed via geometric invariant theory as quotient of some strange action on one-dimensional torus on 3-dimensional projective varieties. We can construct quotients which do not satisfy this property. So this is really not all varieties. These are varieties with A2 property. Okay, so sorry? Right. No, this is not my result. This is a result of Johanna Swięcicka, Polish mathematician, and she constructed such an example, and she proved that there are 2 points which don't have a fine neighborhood. She didn't consider embeddability into toric variety. Okay, and since we like group actions, let us consider group acting on a variety, and we can ask, is it connected with covering? Say, may we find invariant covering? And maybe the most important classical case is a case of toric variety. So if you have a toric variety, then it always admits T-invariant affine covering. And this is a crucial step in the theory of toric variety, because that is why we have the theory of fans. Fan is a finite collection of cones, and these cones, they correspond to such open T-invariant affine subsets. And toric variety, by definition, is assumed to be normal. But if you skip this condition to be normal, then this fact doesn't hold. You cannot find always a T-invariant open affine covering. Say you can take a projective line with a natural torus action. So there is an open toric orbit and 2 fixed points. And you can glue together these 2 fixed points. You will obtain a singular curve with a torus action and with just 2 orbits, 1 point and the complement. And in this case, there is no affine T-invariant covering. So normality is essential here. This is a non-trivial fact. But if we comes from torus to, I don't know, to semi-simple group, to SL2, then even a smooth variety may not have invariant affine covering. Just take complete homogeneous space, and certainly no chance to find some invariant open affine subspace just because the variety is complete and homogeneous. And I would like to mention, in my opinion, very nice fact, which guarantee you which orbits always have G invariant affine neighborhood. This is a theorem of Trautmann, and this is, says the following. You take semi-simple group, you take a closed subgroup, you consider homogeneous space G mod H, or in another words, you consider points whose stabilizer is this H. Then such orbits always in any G variety, if this point is normal, have open G invariant affine neighborhood, if and only if this H is not contained in a proper parabolic subgroup. And this is equivalent to the condition that the centralizer of H in G is finite. And this condition, not contained in a proper parabolic subgroup, also appeared in the previous talk, if you remember. So these are quite natural class of subgroups. Also, there is a notion of uniformly rational variety which take into account action of a torus. You may consider such a covering which is T invariant, construct this and that, and there is a series of papers by Petitjean and Leon de Petitjean on this subject. And now I would like to come from covering to one concrete open subset. So this time I don't ask that the variety is covering by affine space. I'm interested just in one open subset, which is isomorphic to affine space, which varieties allows open embedding of affine spaces. And this question originates, as I learned from Jura many years ago, from a paper by Hirzebruch. Hirzebruch considered analytic situation. He was interested in this paper. He asked two problems about analytic compactification of C2 and analytic compactification of Cn, but with some additional restriction on the boundary because, sorry? Yes, so minimal possible. And there are many papers on this subject. In small dimension 2, 3, there are some classification. For higher dimension, maybe no chance, because there are too many varieties. I would like to mention some Yuri's paper on this subject, as also was mentioned in the previous talk. I also checked the list of publication, and the first paper, yes, it was about rationality of the field of invariance, but also there were two quite early paper by Prokhorov's related to compactification of affine 3 space and 4 space, and some recent paper together with Zeidenberg, which are also devoted to this subject. Sure, sure. Now, these classes are wider. Okay, and let me just make some basic observation concerning which variety may have such a compactification. Certainly, if I have an open embedding of an affine space into some variety X, then X is rational, but this time not necessarily smooth, because boundary may be singular. The divisor class group is freely generated by classes of components of the complement. We know that if you have a affine open subset somewhere, then the complement is a union of divisors. This is unmixed variety. We cannot have components of different dimensions. The complement is always a union of divisors. And in this case, when my affine open subset is a affine space, in this case it's elementary to show that classes of these components of the complement, they generate freely the divisor class group. So the conclusion is that the divisor class group is a finitely generated and free abelian group. This is a strong restriction on a variety. Also, one can easily show that the monoid of effective classes is also free semigroup, which is freely generated by these classes. But these conditions are necessary but not sufficient, and one may find some other conditions, so there is no criteria up to now which characterize existence of such a compactification. Okay, and now I come to the main subject of my talk. I am going to consider maybe just one more remark concerning this, because I was reflecting about the previous talk. It is a very natural problem to, if you have a homogeneous space, G mod H, when it is A-covered. For this is homogeneous, so it suffices to find one open subset isomorphic to a affine space. And then a shift of this subset will make a covering. And Vladimir Leonidovich gave us an example of Hamiltonian affine homogeneous spaces which have this property. And maybe this is very interesting to characterize all homogeneous spaces which have this property, which allow open subset isomorphic to affine space. Definitely this is the case for complete homogeneous spaces for flag varieties. So there are examples of affine homogeneous spaces of this type. Maybe there is a general answer, but I don't know. This is just I'm thinking after previous talk. Okay. But now I'm going to equivariant version. So since there are so many algebraic compactification of affine spaces by complete varieties, maybe we will restrict our attention to some specific class of such compactification. And the good idea is to consider only equivariant compactification. I take some group which acts on affine space, and I ask that this action can be extended to the whole ambient complete variety. And which group should I take? I don't know which group acts on affine spaces, say general linear group, special linear group. But the idea is to take the group of translation. My affine space has a structure of a group, just a vector group. This group is commutative, unipotent. I just add 2 points in the vector space. And this group of translation acts on the affine space simply transitively. And the condition is to consider compactification which are equivariant with respect to this action. So this is an embedding of open embedding of homogeneous space when I consider affine space as a homogeneous space with respect to this translation. Deeper motivation comes from problems of arithmetic algebraic geometry, so-called Manning conjecture, estimates the distribution of rational point of bounded height on the variety via this approach. And there are many works, and these were among the first one, Chamberlain and Chinkel. But this is not my subject, so I will not discuss in this detail. This is just a motivation to study such equivariant compactifications. So just some notation. Firstly, let me recall you that there are precisely 2 one-dimensional connected linear algebraic groups, namely additive group of the ground field and multiplicative group of the ground field. No other. If we are interested in commutative affine algebraic group, then we can take tori, so it means that we take direct product of the multiplicative group. And we can take vector group, the direct product of additive group. And this is well known. I recall that we work over algebraically closed field of characteristic 0. It is well known that any connected commutative algebraic group is just a product of such subgroup. This is always a product of torus and vector group. So these are important building blocks for algebraic groups. And one can show that any connected affine algebraic group is generated by one-dimensional subgroup. So in general, if you're interested in action of an arbitrary affine algebraic group, you can study how its one-dimensional subgroup acts, and this, in some sense, gives you the action of the whole group. So this is an important case. And if we restrict our attention to torus, then we come to a definition of toric variety. This is just an open equivariant embedding of an algebraic torus and dimensional into some normally reducible variety X. And if I want to consider equivariant compactification of the vector group, then I should look for some analogy. Maybe this is some additive version of toric geometry. Maybe we can treat this case the same way as we do in the toric case. But if you will study basic property, you will see that, sorry, no analogy at all. Why? What is important in the toric case? Firstly, maybe not, maybe I will start from the third one. As we already discussed, any toric variety admits an open invariant affine covering. Nothing like this possible in the vector group case, because general lemma, if you have a unipotent group which act on an affine variety, then all orbits of this unipotent group are closed in this affine variety. So if I have an open orbit, and if this orbit is contained in an invariant affine chart, then this orbit is closed in this invariant affine chart. So but this is an open orbit, so this chart coincides with this open orbit. So no chance to include open orbit inside of any invariant affine chart. So if our variety is not one orbit, then definitely no invariant affine covering. So no imitation of this fans, cones is possible. Second bad news is that the number of orbits is no longer finite. We will see the corresponding example on the next slide. In toric geometry, this is also important, that orbits are in bijection with cones, so there are finitely many of them, and here nothing like this. And point number one, this is a non-trivial fact from toric geometry, is that if you have a toric variety, then all action of a tori, of the acting torus, all possible action of a torus with an open orbit are conjugate. So essentially there is only one structure of a toric variety on a given variety. For complete varieties, this is an easy statement, because for complete toric variety, it's known that the group of automorphism is a linear algebraic group. And so the statement is just the theorem that any two maximal tori are conjugate in a linear algebraic group. For non-complete toric varieties, this is a delicate question. This is a theorem by Berthold and use Cox construction, but nevertheless, this is true. Any variety, if it is toric, then the toric structure is unique. But we will see in a moment that such an additive structure may be not unique. So let me give corresponding examples. Here it is. I defined my main player, main object. I will say that additive action on a variety X is an effective action of my vector group with an open orbit. I don't know whether it's a good term or not, additive action. Some people say additive structure, some people say vector group structure or vector group compactification. But term something like toric variety, this is a bad term because in this context, because as I told you, the structure of toric variety is unique, and here you may have on one variety different additive actions. And this is an example. But all of them are conjugate in the automorphism group. Yes, certainly, if you have one action and if you conjugate it by a regular automorphism of your variety, you will obtain another action. But these are equivalent actions. And we always say that action is unique if it is unique up to equivalence. And in this case, I give you an example of two additive actions on projective plane, and they are really different. For one action, I have a line of fixed point, and another action has just three orbits, finitely many orbits. And one action, this is a very naive way to prolongate action by translation to the projective plane, and another action is a little bit more exotic. It includes some non-linear terms in the coordinate of my group, but we will see soon how this action appears. Yes, I will discuss this. They are definitely birational because they have the same open orbit. Yes, yes, they do. I will discuss it on next slide. But there is another technique. It has nothing to do with toric technique, but this is an alternative approach, which was developed in Hassett-Schinkel paper, and let me briefly recall you this. This is about finite dimensional algebra. So let A be a finite dimensional, or if you like, Artinian, commutative associative algebra with unit, just a finite dimensional vector space. Let me recall that algebra is local if it contains a unique maximal ideal, and it is known that any finite dimensional algebra is a sum of local algebras. And the structure of local algebra is also relatively simple. Any local algebra is a direct sum of constants, and this maximal ideal, this is just a hyperplane. And this maximal ideal consists of nilpotent elements, and the complement consists of invertible elements. So the group of invertible elements is a complement of some hyperplane. And also we have an important sequence, decreasing sequence of ideals, powers of maximal ideals, and it vanishes at some point. Say Hilbert-Samuel sequence is a sequence of numbers, the dimension of quotient in this chain of ideals. And example gives you a typical way how to construct such finite dimensional algebra. You take polynomials in some variables, infinitely many variables, and take a quotient by ideal, and the ideal should be the following. If you take any variables, then some power of these variables is contained in this ideal. And this is a necessary and sufficient condition for my ideal to correspond to local algebra. Okay, so this is quite basic. And now theorem, which we called Hasse-Chitkel correspondence, but which appeared independently in two papers, Knopp and Lange and Hasse and Chitkel, different time. But in fact, both Knopp and Lange and Hasse and Chitkel, they proved more general statements. And this is precisely the intersection of their statements. Because Knopp and Lange, they consider not necessarily local algebra. They consider arbitrary finite dimensional algebra. And they establish a correspondence between such algebras and embedding not necessarily vector group, but arbitrary commutative groups. So if you are interested in completion of commutative linear algebraic group, connected commutative linear algebraic group by projective space, so such objects are in correspondence with algebra, but not necessarily local. And the number of local components in this algebra is precisely the dimension of maximal torus -1. And Hasse and Chitkel, they also consider more general situation. Not only n+1 dimensional model of my unipotent group, but any cyclic model of my unipotent group. But what we are interested in this talk, and what is precisely the intersection of these two theorems, is what is written on the slide. And this correspondence is quite basic, so let me explain in one direction. If I have an algebra, how to construct an action. Just take projective space. This is a projectivization of this algebra. The group is just the exponent of the maximal ideal. So this is just your maximal ideal moved by unit. And this group acts on the projectivization just by left multiplication. Our group of invertible elements act on the algebra and on the projectivization of this algebra. Scalars acts trivially, so we have only unipotent group action. And in this case, we have an open orbit, which is a projectivization of this open subset of this group of invertible elements. And the boundary. Boundary is a hyperplane projectivization of the maximal ideal. Converse construction, a little bit more delicate, but also quite straightforward. If you have such an embedding, you would like to construct an algebra. Then basically theory. Again, a bit non-trivial fact. If you have an action of this group on the projective space, then it corresponds to a linear representation. Why? Just because we know the automorphism group of the projective space. This is a group PGLn+1. And it's easy to see that any embedding of a unipotent group into PGL can be lifted to GLN. So we have such a linear representation. Then I take a differential of this representation. It will be a representation of the corresponding Lie algebra. But I'm sorry, group is commutative, so Lie algebra is commutative. This is just a vector space. And the image of this representation will be a set of pairwise commuting nilpotent operators. Then I take the, again, big words, but very concrete meaning, universal enveloping algebra. This will be just a polynomial algebra for commutative algebra. And so I have a homomorphism into the same object, but considered as an associative algebra. And its image will be some commutative subalgebra inside of the matrix algebra. So this is the image of algebra of polynomials. This is some factor algebra of the polynomial algebra. And now, again, some important point. What is a kernel? What is this ideal I which goes to 0 under this homomorphism? This is a set of operators which annihilate all vectors. But this representation is cyclic. This is very easy to check. And our algebra is commutative. So if you have a cyclic representation, then the annihilator of this representation coincides with the annihilator of the cyclic vector. So we see that this is an annihilator of the cyclic vector, and so we may identify this algebra A just, I'm sorry, there should be Kn+1. This is my vector space, this is a misprint. So I just identify my algebra with n+1 dimensional vector space. And this is the algebra I am looking for. And action will be precisely action by multiplication in this vector space. Okay, so this is how this Hasse-Schinkel correspondence works. And now I return to my two examples, and I would like to illustrate them through this correspondence. If you do just by hand classification of local algebra of small dimensions, then you will see that there are precisely two local algebras of dimension 3. The first one is this one, and the second one is this one. Basic exercise in algebra. And by construction, which I just explained, we take a basis of this factor algebra. You take exponent of an arbitrary element of maximal ideal. Computation of exponents in this case is completely trivial because the square of any element is 0. And here we have some quadratic term, just one, because there is only one non-trivial multiplication in the maximal ideal. And I just multiply by exponent an element of my algebra, and I obtain these two nice formulas with additive action. So these algebras are not isomorphic, so we have two different additive actions. Okay, what about further dimension? Also classically known classification of local algebras of small dimensions. Remarkable sequence, 1, 2, 4, 9, 25, what will be the next? You see, next will be infinity. This is a number of isomorphic classes of local algebras up to dimension 6. This is some table we can write down these local algebras. And family starts from dimension 6, and here is the family in this example. Sorry? Yes, this is a family for dimension 7. The modular space has dimension 1 in this case. And this is an example of one parameter family of algebra which are not pairwise isomorphic. They may be isomorphic for some different alpha, but it is proved in the book by Supronenko-Tashkevich that the number of alpha when this algebra are pairwise isomorphic is finite. So for different alpha, only finitely many alpha may lead to isomorphic algebra. Yes, this parameter is responsible for the algebra because this is in the ideal when I take a quotient. This is a quite old from 60s book, this book by Supronenko and Tashkevich, Commuting Matrices, and there is a lot of concrete results, and this classification and this example in dimension 7 may be extracted from this book. Exactly, and this is connected with the family of elliptic curve, and that is why this is a one-dimensional. This is something like G invariant of an elliptic curve. Okay. This I don't know, because we should prove somehow that they are not isomorphic, so we should take something concrete. It is known that the modular space is one-dimensional. Maybe you're right, but there is something written about this in Hasse-Schinkel paper, but I don't remember. Okay, and then concerning conjugacy, what you ask, are they birational isomorphic? If you want to classify birationally action of a group with an open orbit, then the question is trivial. Two actions with an open orbit are birationally equivariantly isomorphic, if and only if this open orbit are the same, right? So in my case of additive action, we always have an open orbit, which is isomorphic to our group, our vector group. So certainly they are birational equivalent and conjugate in the Cremona group. But I would like to say more. My open orbit is a affine space. So if I have two additive action, I may assume this open orbit is always a complement to a hyperplane. So I may assume that for two additive action, two open orbits coincide. And I can change coordinates in this open orbit, which moves one transitive action to another transitive action. Transitive action on the affine space by vector group is unique up to automorphism. So I conclude that any two additive actions are conjugate even in the affine Cremona group. So this is some I don't know, some excuse, because this is bad. It would be such a nice theorem that additive action on the projective space is unique. Imagine two additive action. You act, let me return.
Just say automorphism of ends, please. Right?
Yes, so for any additive action, you, the complement to the open orbit is this boundary, right? This is just a hyperplane. So if you have two different additive action, you may put one on the other, this open orbit. You may assume that open orbit is the same. So it means that they are conjugate in the automorphous group of this open orbit. And this is the automorphous group of the affine space, so-called affine Cremona group, right? So this is somehow trivial. But you may ask, what is the conjugating element? And the answer is here. So this is again from the Hasse-Chinkel paper. Take algebra of polynomials in n+1 variable, and take a subspace inside of this algebra, which is firstly n+1 dimensional, secondly is invariant with respect to translation, and thirdly generates this algebra. Okay? So you may take linear span of variables and unit. It works. But there are other basic subspaces. And Hasse-Chinkel observed that this is a way to classify local algebra, that n+1 dimensional local algebra are in bijection with this basic subspaces. And let me explain this correspondence in one direction. If you have a local algebra, then you take just an exponent, the exponent of an element from the maximal ideal. Exponent is again some element of maximal ideal plus 1. And coefficients are some polynomials. So this is not immediately obvious, but this is checked in Hasse-Chinkel paper, that 1 and this n polynomials, they span such a subspace. And conversely, any such subspace corresponds to local algebra in this sense. Okay? So my observation is that these polynomials are precisely the coordinates of the automorphism which conjugate one additive action to standard additive action. I'm sorry, maybe I should return. By standard additive action, I mean this. In any projective space, you may just imitate translations this way. This is a standard additive action. So the claim is that such a automorphism of the affine space send you any additive action to a standard additive action. And the proof is straightforward. Let me just explain you. I take an element from the open orbit. Open orbit may be considered as 1 plus maximal ideal. And I take exponent, standard action. This is just a parallel translation. And my new action is just a multiplication by exponent. It is here. And one goes to another by applying this automorphism. And so what is the conclusion? Take affine Cremona group. Take subgroup in this group which corresponds to this action on projective space, to the standard one. And consider all subgroups which are conjugate to the standard subgroup. And this big conjugacy class in the affine Cremona group intersects special linear, general linear group, which is an automorphism of projective space, in some conjugacy classes of different additive action. And this is exactly reflected here. Okay, what to do? mouse. One more. Okay, work. And also some elementary observation. I'm sorry, when I produced this presentation, I don't know why, but I was unable to compile proposition. I was able to produce either theorems or lemmas. So some some statement should be proposition, but I have only theorems and lemmas. I'm sorry. Firstly, you may be interested in additive action with finitely many orbits, and it was observed by Hassett and Chinkel that such an action is unique. And it corresponds to one generated local algebra, which is also unique. Also, let me recall you a definition of Gorenstein algebra. This is an algebra whose Sokol is one-dimensional. It means that, firstly, Sokol coincide with the last non-zero power of maximal ideal, and secondly, this last non-zero power should be one-dimensional. And to be Gorenstein means that the corresponding additive action has a unique fixed point. This Sokol will be a unique fixed point. And also, why to consider additive action? This may be useful in studying conjugacy of some maximal subgroup. Say, when you study theory of linear algebraic group, you have very nice theorem. All maximal tori are conjugate. All Borel subgroup are conjugate. All maximal unipotent subgroup are conjugate. And you may expect that all reasonable maximal subgroup are conjugate. But this is not true. If you take all maximal commutative unipotent subgroup, then they are not conjugate. You may construct many, many non-conjugate maximal commutative unipotent subgroup. They even may have different dimension. And actions with open orbit is a good way to construct such maximal subgroup. This is an elementary observation. If you have a commutative subgroup which acts effectively with an open orbit, then this is automatically a maximal commutative subgroup. Here you don't need even unipotent or something like this. This is always the case. So different additive actions give you different maximal commutative unipotent subgroup inside of the general linear group. But you may construct a maximal unipotent subgroup of different dimension, and they will not come from additive action. Subgroups coming from additive action, they are always n-dimensional. So the classification of maximal commutative unipotent subgroup is still mysterious. There are many papers, many results, but no complete classification. And now I would like to move from the case of projective space to the next case, projective hypersurfaces. And this is also can be treated via Hassett-Chinkel method. And in this case, we have extra data. I always assume that my action is reduced. So the action on this projective hypersurfaces comes from an action on the ambient space. And then, this is not a serious restriction. This is almost always the case in some sense. It can be made precise. And then, this is already a result, that this action of smaller unipotent group, which has an open orbit on this hypersurface, comes from action of a bigger commutative unipotent group, which is an additive action on the whole projective space. So any such hypersurface is obtained as a closure in the projective space of some codimension 1 subgroup in my n-dimensional commutative unipotent group, which acts with an open orbit on projective space. And this is just encoded in this data, algebra A, and this some subspace which generates this algebra. And in this way, my former student, Elena Sharoyko, proves that any smooth quadric admits a unique additive action. Construct an additive action on a smooth quadric, this is quite obvious thing, but Hassett-Chinkel, they ask in their paper how to classify all such action, and maybe there is also some Hassett-Chinkel correspondence in this case. But no, such an action is unique. And it has a quite nice linear algebra type proof. Elena introduced some symmetric non-degenerated bilinear form on this algebra, and it can be proved that if such a form exists, then this algebra is unique and subspace is unique. And also there are some further results on degenerate quadrics. For degenerate, there will be many additive actions, but they also can be studied. Our recent result is about normality. Smoothness is quite elementary, so I'm sorry for the theorem here because I'm unable to make propositions. The only smooth projective hypersurface with the additive action is smooth quadric. Hyperplane as well, but this is somehow degenerated case. And concerning normality, we check it just now. This is a bit more delicate result. So I take an equation of my hypersurface. Here it is. The first coordinate, z0, this is a coordinate corresponding to this boundary hyperplane, to the maximal ideal. And I just consider polynomials which are given in this expression. And I'm interested in last two polynomials. I consider the decomposition into prime of the last polynomials divided by the product of irreducible factors, and the condition of normality is the condition that these two polynomials are coprime. Smoothness, sure. Smoothness is a well-known fact because automorphism groups. So yeah, this is what I said, that I'm sorry for this theorem because this follows from that almost always the automorphism group is finite, so no chance to have additive action. But normality is a delicate statement. Sorry? So let me return. It depends. You just take your polynomial fd and decompose it into prime. So you have some prime factors and some exponents. It depends on the polynomial. I will show that these polynomials may be quite arbitrary, so I will come to this soon. Okay, now let me just give a definition that a hypersurface is non-degenerate if it is not a projective cone over some other hypersurface. If it depends on all variables, we cannot make a change of coordinates such that the equation of our hypersurface does not depend on some variables. All this can be easily expressed in terms of partial derivatives. So, two observations. The first one is that non-degenerate hypersurface, they correspond to some local algebra, and you may ask what is the condition that the hypersurface is non-degenerate. And this is precisely the condition that this algebra is Gorenstein. And this subspace, which appears in this classification, this is exactly the complementary subspace to this one-dimensional circle. And the result, which I like, is the condition of uniqueness of additive action. Additive action on a projective hypersurface is unique. I don't consider hyperplanes. No, hyperplanes is degenerate. If and only if this hypersurface is non-degenerate. We prove it in two papers. We, together with Yulia Zaitseva, prove that if it is non-degenerate, then the action is unique. And Ivan Beldiev proved it other way around. For any degenerate, he constructed at least two different additive actions on this hypersurface. Next step about the degrees. Again, it's quite easy to check that this hypersurface cannot have arbitrary degree. Its degree is at most n, where n is a dimension of the ambient projective space. And Ivan check that for any n, for any d between 2 and n, there exists a non-degenerated hypersurface of this degree which has such an additive action. And also, if you take extremal cases, first extremal case, this is the case of d equal 2, and in this case we have non-degenerate, which means smooth quadric, and by Shoroyko theorem, additive action is unique. And if you have another extreme, if you have d equal n, then it turns out that such a hypersurface of maximal possible degree is also unique. And this is unfortunately not normal, this is quite specific hypersurface. And what about the boundary? So if I take a projective hypersurface with an additive action, I can ask what is the complement of this additive action. In the case of projective space, the complement to the open orbit is very easy. This is just a hyperplane. But it turns out that in the case of projective hypersurface, the boundary may be as difficult as you like. So firstly, a boundary is always a projective cone over some other hyperplane. And vice versa, you can take an arbitrary projective hyperplane. Then there is a bigger projective space and a hypersurface in this space such that the boundary of X is a projective cone over this hypersurface Z. So in some sense, up to taking projective cones, any projective hypersurface may be realized as a boundary of some another projective hypersurface with respect to the additive action. Okay? And so here I stop with the case of projective space, with the case of projective hypersurfaces, with the Hasse-Chinkel correspondence, and let me study additive action on other variety using other technique. I would like to start with flag varieties. Flag varieties, this is just a rational homogeneous space, or complete homogeneous space of a semi-simple group. So this is G mod P, where P is a parabolic subgroup. Examples are Grassmannians, flag varieties, full flag varieties. Again, quite easy observation that if we restrict our attention to complete variety with a reductive automorphism group, then it admits additive action if this is a flag variety, no other candidates. But certainly there are complete varieties with not reductive linear algebraic group. Okay, how to classify additive action on flag varieties? Firstly, existence. Let me recall you what is classically known, maybe from Demazur, that some flag varieties are isomorphic. And this is a complete list of possible isomorphisms when two flag varieties are isomorphic as abstract varieties. And also there is a nice list of parabolic subgroup whose unipotent radical is commutative. Here it is. And if you know that the unipotent radical is commutative, then certainly our flag variety has an additive action. This is just Briard decomposition. Unipotent radical of parabolic subgroup acts on this homogeneous space with an open orbit. So if it is commutative, then it is an additive action. And the question is it true that this is the only case to have additive action? And it turns out that answer is yes and no. No, because there are flag varieties with non-commutative unipotent radical of the parabolic subgroup, which have additive action. But the reason for this is only this isomorphism. In all this pair, it turns out that for bigger group, we have a commutative radical of a parabolic, and for smaller group, we have non-commutative radical of a parabolic. So these are the only exception when we have additive action and unipotent radical is non-commutative. So exceptional, I mean that this is a small part of this isomorphism. Okay, what about the uniqueness? It turns out to be a difficult question. It was addressed in a paper by Fu and Huang and independently by Rostislav Devyatov. And the answer was surprising. This is an extension of Sharoyko's theorem, that the additive action on flag variety is always unique. The only exception is the case of projective space, when we have many actions by Hasse-Chinkel correspondence. In all other cases, we have a unique additive action. And these two papers, they have completely different proofs. And very interesting, very good results. And there were some attempts to generalize it. Say, Korean mathematician extended to non-commutative unipotent group, when we have a Briard decomposition, and when the unipotent radical of parabolic is non-commutative, then also one can prove that such an action is unique, no other action with an open orbit. And in parallel, independently, and even earlier, Zhenya Fegin constructed degeneration of flag varieties. So if we come back, this list of parabolic subgroup with commutative radical is rather short. So all of them are maximal parabolic subgroup. So for almost all flag varieties, for any non-maximal parabolic subgroup, we don't have additive action. But we want to have additive action. We like additive actions. So Zhenya constructed a degeneration of flag variety to some another variety, which admits an additive action. And it turns out to be quite interesting quasi-homogeneous projective variety with many remarkable properties. Okay. Now I would like to say briefly about toric varieties. If we have a toric variety and we want to study additive action. Firstly, let me say that a complete toric variety is radiant if we have a maximal unipotent subgroup inside of the linear algebraic group out X, and if this group acts with the open orbit. Or this is the same as to say that some unipotent group acts with the open orbit. Also, I would like that my additive action should be somehow compatible with the toric structure. So, compatible, I mean that the image of this commutative unipotent group is normalized by the acting torus inside of the automorphous group. And finally, I would like to give a definition of specific fan. These fans, they look like this. You have positive octant somewhere here. Oh, never change anything. So you have somewhere here positive accent. This is one cone in your fan. And on all other rays, they live in the negative octant. And all cones looks like this. This is a definition of the specific type of fans. And theorem that the following condition is equivalent for complete toric variety. Some unipotent group acts with the open orbit is very strange. It is equivalent that commutative unipotent group acts with the open orbit. And this action of commutative unipotent group even can be assumed to be normalized by acting torus. And this happens only exactly for such specific fans. So we have a combinatorial description of these varieties. Okay, and now there is one more attempt to characterize varieties with additive action. This was proposed by Fu and Huang. They called it Euler symmetric varieties. They said that a projective toric variety is Euler symmetric if this variety has many actions of one-dimensional tori. For any point, you can find an action of one-dimensional torus such that this X is a fixed isolated point, and the action on the tangent space is just a scalar multiplication. Look here in the definition of Euler symmetric varieties, there is no additive action, no unipotent group. But it turns out that this is equivalent to admit an additive action. And in fact, this implication, if we omit toric, then it will hold in one direction. Any Euler symmetric admits an additive action. And it seems that this is close to existence of, to characterization of varieties with additive action. Okay, time is almost over. Here's a list of results of members of our research group on this subject. Here, Sergei Junusov classified toric surfaces, which admits two additive actions. For toric surfaces, complete toric surfaces, there are either no additive action or one additive action or two additive actions. And Sergei classified those which have two. And also here, in arbitrary dimension, classified toric varieties which have unique additive action. Kirill Shakhmatov constructed compactification of a affine space equivariant which is not projective by a smooth toric variety. And Anton Shafarevich classified additive actions on toric projective hypersurfaces. All of them turns out to be degenerate quadrics. And also I would like to mention a classification result by other people. Two-dimensional cases, singular del Pezzo surfaces, three-dimensional cases, and in arbitrary dimension, but with some condition on the index of variety. And these are some lists, something like 13 toric and 4 non-toric. But this result I obtained from some bigger classification. People just go through this bigger classification and take those which admit additive actions. And very briefly, I will say the question which I'm thinking about. Certainly, you know this nice theorem that the variety, complete variety is toric if and only if its Cox ring is a polynomial algebra. Maybe in some similar terms classify additive actions, not known. Algebraic transformation group, take an arbitrary commutative connected linear algebraic group. Classify it affine embeddings, open affine embeddings. Too many, okay, factorial open affine embeddings. Seems to be doable, but not done. we know which complete toric variety admits a unique additive action, but maybe it admits finitely many or infinitely many. And for this, we have no criteria. Also, for finitely many orbits. For projective space, there is only one additive action with finitely many orbits. But what about other toric varieties? Anton Shafarevich now is working on this. Classify additive actions on weighted projective spaces, some weighted Hasse-Chinkel correspondence, done in dimension 2 and 3, but no general answer. Because otherwise one can check that there will be, sorry, let me go back. Because if you don't have this one, then there will be no additive action. You should have one chart with a affine space, and this is guaranteed by this one. Okay, then about maximality, is it true that any maximal commutative unipotent subgroup of correct dimension of the dimension act comes from Hasse-Chinkel correspondence? I don't know. And this is also that any maximal commutative unipotent subgroup comes from some action with an open orbit. Also, I don't know. And Fu Huang asked about Euler projective, that this is a characterization of varieties with additive action in the class of smooth Fano varieties of Picard number 1. And just a list of some publications on this subject. There are quite many papers on this. People publish during recent decade. So this is all. Thank you very much.
Any questions?
So I have a question. In your theorem with Popovsky that you formulated, and the conclusion was a flag variety, do you assume from the beginning that the complete variety is smooth?
No, I was wondering who is asking this question. This comments come from heavens. And then I realized this is Mikhail Grigorievich from internet. So let me return to the slide. This modern technology, this is really no. Let me look. This is about flag varieties. So this should be here. No, I don't assume that this variety is smooth, and I can explain this. Assume that our automorphism group is reductive, and it admits additive action. It means that I have a commutative unipotent subgroup inside of my automorphism group, which acts with an open orbit. But then maximal unipotent subgroup acts with an open orbit, because this is a bigger unipotent subgroup. And in the theory of spherical variety, this is called spherical variety of rank 0. Because spherical variety, this is the case when Borel subgroup has an open orbit, and inside of this open orbit of Borel subgroup, there are some smaller orbit of maximal unipotent subgroup. And their codimension is called rank. And if even unipotent subgroup acts with the open orbit, then this is a rank 0. And this is known that the only spherical variety of rank 0 are homogeneous flag varieties. So this is true without smoothness assumption. I don't know whether I answered to heaven. But...
Thank you. Thank you.
Sorry? Normality. Spherical is normal, for sure. No, for this theorem, no, because I may up to take normalization, move, and then, even we check this in our proof, that it cannot come from a homogeneous space, nothing else than this homogeneous space. So normality is not required.
Do you know anything about the edge cases where it's from here, it's not from heavens? I'm here.
But you also have this device. So
I have the device, yes. So it's almost from hell. Question from hell. Do you know anything about the product of copies of GA with one single GM and vice versa? Like, there are edge cases between the multiplicative torus and the...
Yes, we do. Thank you for this question. Let me go to this list. This is the case, we call it co-rank 1. Co-rank 1 means, maybe this is the opposite what you asked. When you have, this is many toric factor and one additive factor. In this case, we also have a theory for embedding of this type. But when it is completely general case, then this is problem number 2, which we don't. No, this is maybe as difficult as a general case. Because when you have an open orbit of unipotent group, you have some technique. But when you have a codimension 1 or orbits of unipotent group and you have some extra transversal torus, I don't know how much does it help.
Okay, some more questions?
Last theorem. It's not the last. Fano. You mean? You mean this one? They also use some classification of all varieties of Picard number 1. Yes, they go through the list.
I have one more question. If you consider conjugations that send standard additive action to arbitrary one, how often this map is toric?
You mean this conjugacy in affine Cremona group?
Yes.
I don't think so. So this is quite difficult polynomials. Non-monomial, non-toric.
So never or almost never?
I think never. I didn't check, but I am almost sure never.
Okay.
More questions? If not, let's thank the speaker again.